you have to look along the side of it or under it or whatever, you realize we had a challenge. Somebody suggested we could get around the problem by making it a single lens reflex. It sounded like a good suggestion, and I made a little cardboard model of such a thing with a reflective Fresnel lens. We took an Edmund Scientific Fresnel lens and put a coating of aluminum on it and stuck it in there, and we had something that wasn't very good, but if you looked in top, you could see what looked like the picture. Now there were some problems with it. It was distorted, it was dark on one end, and it was upside down. We didn't know whether that would sell. So we went through some thinking about how to do it, and this is kind of what resulted. I don't want to take you through too many of the blind alleys and the early experiments and things, but I want to tell you what this does, how we got there, and how we made the parts. In some cases, how we tested the parts, because some of them are preforms, 2 of them are freeforms that have a lot in common with things like wavefront encoding, masks, and other things that are being done. Only this was done very long time ago. I mean, I think people were using freeforms earlier for spectacle lenses back into the 1950s, but they hadn't gotten popular until a little bit later. They were still creeping along. And the manufacturing technologies that made all these things, including the software, were also kind of creeping along at a very slow pace. And we kind of had to do what we could do each year to make the different steps. So that's what this is about. This is unusual freeform and structured optical components in commercial camera products. This wasn't the only camera. We got 2 more I'm going to mention. And then there's a chunk toward the end, represents a talk I'm going to give next month to the ASPE in Charlotte that is about manufacturing freeform lenses and structured surface lenses for use in the far infrared. There's been a lot of interest in things like uncooled bolometric arrays that give you a digital image way out into the infrared. And people are using that for getting thermal infrared pictures of things for various purposes. If you do a Holmes inspection on HGTV, you'll see Mike Holmes taking his little infrared photograph to see where your insulation is leaking heat. These have reached the popular culture to that level. But there are a lot of applications, military, domestic, police, you name it. You can buy these things, I think, for personal use. Edmund was selling one in their catalog a couple of years ago. So that's what this is about, and I'll tell you how that's done and why I think it might lead to some new things. This guy is a former boss of mine, Edwin Land, who's holding up a Polaroid SX70 camera. Not the first, it was a little bit after the first, but basically you get a picture that comes out of this thing and develops while you watch it. Takes a few minutes, but you get a final picture, and then you stuff it in your album, and all the garbage, the negative and all, right in there with it, so you don't need to throw that away. But that's what the camera looked like, and it was a big seller. I mean, we sold something like 7 million of these things over a period of maybe 14 years, and then came back and sold another 500,000 later. But that's what the thing looks like. This one obviously has been ripped open so you can see what's inside it. And right here you can see the things I'm mainly talking about. This is a structured surface, I'll explain in detail. This is a freeform lens, and there's a freeform lens mounted right there as well. This is the back of a concave mirror you can't see from here. It's not a freeform, it's a figure of revolution, so it's not as interesting, but I tell you what it does. This is a taking lens. These rollers process the film when it comes out. Now what you see is in the viewing posture. What you would see here is a picture. You'd see what the camera was going to take a picture of. The next couple of things that happen after you touch the shutter button that's been cut away is this thing pops up. There's another mirror on the bottom of it. So light from that lens can then hit the film that's underneath. All right, so that's what it does. That's the system. Now, this is a picture I stole from Life magazine. It was taken by a famous photographer named Fritz Coro. And the idea is that different colors of light coming in from different angles in the front go through the taking lens and make images in different places on the focus screen. And then the light gets picked up. It all gets regathered again. The different colors come together, reflects again, and goes through the little hole, spreads out in the concave mirror, gradually converges toward the eye lens, crosses over right here. That's where you put your eye, so you get the whole scene in at once. Now, if you're looking at this carefully, you realize that there's a bit of a swindle going on. The light obviously was sent through the other way to take the picture. And the way you can tell is where the light hits the focus screen, it spreads out after the reflection and not before. So that was done with 3 laser beams. Legend has it they took the picture by having somebody smoke a cigar very heavily and blow a lot of smoke into the scene to get that foggy look, and everybody else was gasping for breath at the time this was happening. But this shows what the product looks like inside. I've got a separate view just showing the focus screen and what it does. This is the tungsten light bulb taking the place of the taking lens as a source of light, and it's spreading light over the entire focus screen. And that light is regathered. I think you can see a spot here on the piece of paper where it's brought back together again. So one of the things the structured surface has to do is behave like a concave mirror and make an image back on its own side to regather the light. But it's also spread out that light a considerable amount. Without that, it wouldn't be a focus screen. You'd be focusing your lens and you wouldn't see anything happen because your eye would accommodate to the changing image. Now this is an artist's view of what that focus screen looks like close up. It's a Fresnel type surface with a bunch of sloped facets. Now those are 5/1000ths of an inch wide. And in order to make the texture look good and not like gravel on your driveway, we have to keep the irregularities that are put on there down to about 1/1000th of an inch across. So one thing you can be thinking about for the next 10 or 15 seconds is, how do you do that? How do you make a surface like that that's just got this kind of irregularity on it at the same time it's on a Fresnel? I mean, a lot of things you can't do to Fresnel. You can't scrub it, you can't drop ball bearings on it or anything like that. You've got to do something else. And we did something else. And there's a micrograph of the actual picture. That's what they call an Epi-Nemarsky micrograph. And what's interesting about this is the numbers, because not only did we have to put the structure over the entire surface of each of those tilted nested facets, but the structure itself is shallow. It's only half a wavelength deep, and that has to be controlled. It has to be controlled because if you make it any shallower than that, it tends to go away. You have what the diffraction grating art would call a zero order that never goes out of focus, or never gets blurry when it goes out of focus. And you don't want that because that would be very bad in a reflex camera. An interesting technical aspect to this is that if you reflect light from a half-wave irregular surface like that, you got a full wave of irregularity because reflected off the peaks and the valleys is the whole wave of difference, right? Now suppose it were transparent, and suppose it weren't reflected, but just a transparent piece of plastic exactly like that with an index of about 1.5. The light going through gets only a quarter wave irregularity, right? And you know about Rayleigh, you know that in a quarter wave, it's not even diffuse. So we're working right at the cusp where physical optics and geometric optics come together. And I made something to help dramatize that. I prefer not to pass it around because it's fragile, but I'll hold it up and show you the activity of it. I made this with a little help from our shop. We made a surface that had the same irregularity on a flat. And what's nice about this is this was pressed plastic against a metal surface. Half of it's covered with aluminum. If you look at the aluminized half in the mirror, you can hardly recognize yourself. Certainly couldn't shave by it. If you look through it, you can read a newspaper because the transmitted image is quite sharp and the reflected image is terrible. Now, why is that? It's because it's right at that level where diffraction heals the transmitted image, quarter wave, and the reflected image is still disturbed by a whole wave. So you got geometric optics coming out one side and you've got physical optics helping you on the other side. That's just interesting because of the way the numbers came out. We don't use that feature in the camera. But how do you make a surface like that? That's what's interesting. A lot of possibilities that we considered and dismissed. What worked was, I'll make it sound simple because I'll tell you the answer right up first. We had an original ruling, which I think was on either aluminum or bronze. That ruling was electroformed to make a tool that was used to press plastic, and you can alternate as much as you want between part geometry and tool geometry. It turns out that there's some plastics that you can affect with some solvents that will do the following. And what I like to use was cellulose acetate butyrate, could have been polycarbonate, could have been a couple of other things. Cellulose acetate butyrate is used for things like blister packaging, or used to be before people discovered that cellulose acetate propionate smells better. If you hit this with a drop of solvent, the drop of solvent will hit it, wet it, dissolve a little bit of it, and then evaporate and leave the surface behind. Now what's interesting, if you provide these drops with a little airbrush like an artist would use, you can make a fine spray of just the size you want. And of course it's not one drop, it's a zillion of them. And they keep coming. And as you do this, you reach a certain level that doesn't change anymore. And the level you want is half a wave deep, it's about this big. And oh yeah, you care about the slopes. For this application, you want the slopes to be out to about 2 degrees and no more, and not much less. So we want to control the slopes, the size, and the depth, as well as the cosmetic appearance, no fingerprints, right? So you can imagine this didn't work the first time. We had to try different solvents. And one of the key issues turned out to be a later surprise. If you just use the solvent, it doesn't work terribly well. If you mix about 1 part per thousand of a different plastic, like acrylic, dissolved in the solvent and do it, you get a much better result much faster. Why? Maybe it's a wetting agent. I don't know why. I just know it works. I thought to myself, what would happen if I replaced that 1 part in 1,000 of acrylic with 1 part in 1,000 of the same material, cellulose acetate butyrate? And the answer is it makes a pretty good focus screen for a different F number. The slopes are different. So little things can matter a lot. And I thought, I know what Thomas Edison went through with all those little filament materials before he found carbonized bamboo. But sometimes you're doing this high technology stuff, it's not all in the computer. And I'm happy that it worked. Essentially the right thing worked that we did the first time, but it took some other trial materials to get there. Some materials that would dissolve in the solvent don't work at all. I can make an acrylic lens and spray it, nothing happens. So like I say, you got to get it all right. Now, I mentioned the 2 degrees. Let me show you what's happening here. Here's an old-fashioned view camera. You've probably seen these. There's the camera lens, there's the focus screen, there's usually some kind of a Fresnel field lens. Then there's an eye lens in your eye, and you only need the eye lens if you're coming in close. If you're the old timer with the big glass plates and the black cloth, you don't need the eye lens because you can see it okay. All right? But what you're really doing is taking this rather small bundle of light that's going to your eye, and you're trying to get samples of light from all parts of the camera lens. Because if the focus screen isn't diffuse at all, your eye is going to get light only from the center of that camera lens. You see why? The angles are going to follow right through. So the main function of the focus screen is to make the out of focus image look blurry. And it's got the secondary requirement to keep your eye from accommodating to a moving image. It's got to do those things or you can't tell where to focus your camera. So I looked at that and said, well, let's pretend the light's going the other way. We're going to replace the eye with a laser beam and hit the focus screen. What we want the focus screen to do is to spread the light over the aperture of the lens. And that can be described mathematically. You make some assumptions and do calculations. And I want to do 2 things. I want to make it as blurry as I can get it without losing too much light, and I want to get as much light through as I can. This is one of those cases where something went right. And what went right is, it turns out that if you consider different amounts of angular diffusion, it's possible to get 84% of the possible blur. At the same time, you've still got 84% of the possible brightness. So if you get it right there, it looks bright and it does its job. If you go way over to the right, it's dim, doesn't get any blurrier really. And if you go all the way to the left, it's only a little bit brighter and it's not helping you tell you're out of focus. See? Now, I have to admit that the analysis was all done after we'd finally made some good focus screens. You do this so you can publish it, right? But empirically, what I did was I was looking at a bare light bulb over my head while I was doing this and trying to guess how big a spread I wanted. After I had it, I did the math. But it worked very well. So that is in this position. It takes the light from here that hits all corners of it, brings it all back together through there, and it comes out. Now you want to see it. And that requires turning the image right side up and presenting it to the eye. The light that's regrouped going through here hits the concave mirror, and it gets re-imaged in this place in space. Now let's suppose for a moment that the concave mirror is an old-fashioned spherical shape. You get a pretty decent looking image, but it's got a problem. The problem is it's supposed to be a pretty square, and the top quarters are all mushed down. Very bad case of distortion. So that's not good. Well, there's a way to fix that. If you imagine that as being part of the peel of an orange and flattening it back a bit at the top, you can raise those corners. That's what we did. It's an A-sphere. It's an A-sphere of revolution. Kind kind of like an ellipse, but not quite. Its axis is actually slightly outside of the part down here, about like that. And it's a molded part, coated. And like I say, it's not a terribly interesting A-sphere because it has symmetry. And it makes a nice image in between. But something happened, because when you make the top flatter to bring the corners up, you're also moving this image off to the right compared to the bottom. Tilt. If you stuck a postage stamp in there and tilted it like that, you'd have what we saw. The top of the image appeared to be about this close to the eye, and the bottom of the image was out past infinity. Now, Edwin Land, who was already at the time getting elderly, pointed out to me that as a young kid I didn't appreciate the fact that he couldn't focus over the whole surface. It saw only one arch that was reasonably sharp. And it dawned on me that the problem was the accommodation of the eye. I still had it. He didn't. I was 30 years old. He was, what, 30 years older. Makes a difference. That's the accommodation needs of the eye. So we knew we had a problem, and I thought we ought to be able to do the solution the same way you do a spectacle lens. So we tried a bifocal. We tried a trifocal. It looked terrible. And I thought, well, maybe there's something else we can do. It's like a progressive. It's where the power changes gradually from top to bottom. I'm wearing a pair. A lot of you guys are wearing them. They've been around for a long time. I had to explain to the shop what I was trying to make and why they couldn't make one on a lathe. So I made this out of plastic. That's just a plastic frame. It's got an acrylic back. It's got something like saran wrap on the front, tight, stretched tight. It's full of water. You hold this thing level and you look at your feet, it looks like a flat window, right? And you tip it up, the water tends to run down to the bottom. It makes that a positive lens, it makes that a negative lens where it's been left behind. That's a free-form surface. It's got no axis of symmetry. It's got a negative area, it's got a positive area, and that's the kind of thing I need. Now, I can't just put this on the camera because for one thing it'd be upside down. I want the positive part at the top and the negative part at the bottom. But I did make some this way by putting epoxy under saran wrap, letting it sag, letting it get hard. When it was hard I could turn it around. And that was a big help, so that encouraged me that I was on the right track. So that's what it does. So let's talk about details a bit. This is what it really looks like. It's exaggerated a bit, but that's the shape we actually put in the camera. You notice it's convex up here, concave down here, and slightly more complicated things are happening. That's a sixth order polynomial shape. And the first ones we made weren't quite that complicated. They were third order polynomial, and we did it with a lot of metal plates stacked up and a pantograph machine to take this big model and make a little lens of the same shape. And that was encouraging. I'm leaving out a lot of little midpoints along the way. But that's the shape we used, and we had to learn how to make them. But there was something else that happened that was kind of important that I'll come to too. I point out that when you're making one of these, the tool path isn't the same as the shape of the part. You know, in most obvious form, when you're cutting the convex part of the part, you add this radius to the radius you want to cut. And when you're doing the concave part, you subtract. Well, for a freeform that's complicated, you do different things in different places in 3 dimensions. And, you know, John Mader here conducted a lot of that for us. But we were able to work out the path for the machine that would do exactly that. Let me regain the place here I lost. Okay, there it is. We programmed machines to do this. We went through a bunch of different things on different machines. But basically you take some kind of a grinding head and you've got a piece of stuff that's going to be your mold tool and you make a lot of passes across it and you tell it how to cut. And back in those days, the way you told it how to cut was you put your equations in a time-sharing computer and you had a little tape punch that was making a noise punching out a long paper tape that you were going to feed into the machine controller. And the real challenge was to get the whole tape made before there was a telephone noise impulse that came through and screwed up the tape and, you know, made the grinder go through the part or something. So it took a while to get that right. There's been a lot of progress since those days. First we had paper tape and then we used Mylar tape and, you know, how much tape do we finally have? Miles of this stuff. We used to use a Model 35 teletype to punch it out. Right? But the results were good. You could polish it up without much trouble and make a free-form molding tool that would mold that shape we need for the eye lens. And it worked. It got better with time. Now I might comment that in making these, you had to somehow have a way to tolerance it and to measure it and know whether it was good enough. And whether you could stop leaning on the opticians to make it better, whether you were already there, and after you mold parts to know whether the parts were good. And since this was an eye lens, I used ophthalmic tolerances. What we have here is 7 profilometry passes across that piece. And it's an interesting thing you can do. After you've recorded all the data from this, you can pick any little cluster of 9 points like I've illustrated there in many places on the area. And for each one, you know what the error is compared to what you think you should have had from your equations at that place. You take those errors, and I've identified them by letters, A, B, C, D, E, F, G, H, I, and you do a little calculation from those letters. You know, subtract them and all, and delta is just the width between those two. You divide by that. What you get is second derivatives, partial derivatives of that surface for x and y and diagonal. What the diagonal does is to tell you, this one, it tells you how much cylindrical power you've got that's going diagonally that doesn't show in the other 2 terms. All right, now you put these together the same way you would for an eye lens, for an spectacle lens. These came out of an old patent by a guy named Quinault back in 1959. The local spherical power, in this case error, you get by combining those terms, and the local cylindrical power you get by combining these. So you can apply a tolerance by saying, we're going to keep polishing this baby until we get down to better than an 1/8 of a diopter of astigmatism everywhere and a 1/4 diopter of sphere. Right? Real simple, real straightforward. But that was an early freeform surface that needed tolerancing. Different freeform surfaces for different purposes may need to be measured and toleranced in a different way. That worked for us. All right, now back to the product. We've got the eye lens, we've got the mirror, there's an image. Problem is you look through it and you discover when you ask people that the people looking through it fall into 2 populations. They're the ones that say we make it better and the ones that say we made it worse. And if you study these 2 populations, you discover the ones for whom it's better are the old guys and the ones for whom it's worse is the young guys. Now why is this? We're talking straightforward optics. The old guys have an accommodation problem and the young guys don't. What we've done by this is to take a problem we have because of the changing shape of that surface and now the changing shape of this surface. And we're asking the top of the eye and the bottom of the eye to focus at 2 different distances. That's called coma when it happens in a lens. The eye doesn't have any muscles for dealing with that problem. You could make a contact lens and slip it on the eye, but we didn't think the customers would go that way. The old guys noticed that we got rid of the field tilt. They loved it, and they were willing to accept some coma. The young guys who never had a field tilt problem noticed the coma and said it got worse. Right? We had to fix it. And how do we do that? Well, you notice that this aperture stop gets re-imaged onto the eye. So instead of putting the contact lens on the eye, we'll put it here at the aperture stop. It's another freeform lens. It's a much smaller one. Tom, it's the one I gave you this morning at breakfast. Same thing. But that's what it looks like, and it's a relatively simple shape that's convex and concave. But over that rather small diameter, of not much more than 1/10 of an inch, is a power change of close to 18 diopters. And the whole thing has a vertical relief of only about 2/1000 of an inch. So it's a rather remarkable little freeform, and it wasn't all that trivial to make, but they were very easy to mold. They were all good. Anyway, if you just shine a laser through a thing like that, you got a spot on the wall. It just shows a beautiful coma pattern. Pretty anyway. Now, if you're going to make parts like this that involve molding, you need a very strong workbench to start with. And you make a steel mold with a lot of plates and a lot of holes for all these optical components that are in place when you're squirting plastic into the mold. If you do this right, you can mold your lenses maybe 24 at a time for no extra cost. You've made the tools, you've got the freeform shape in there. The molding machine doesn't care whether it's freeform, it just gives you lenses. They come out, yes, they're already polished. You don't need to polish them. Somebody always asks. But you take them out, you essentially break them off or shake them off of the runners, and you've got the part. The little parts are even easier. That's what the piece, excuse me?
What's the optical use of a large dead blow hammer?
Is which?
What's the optical use of that large dead blow hammer? What's on the table?
Oh, probably putting the whole back together. I forgot that was in the picture. Big hammers are very important for making precision adjustments. A lot of people don't appreciate that, but if you want to put something exactly the right place, you bolt it down tight and hit it with a hammer. And the reason is you get a very large impact force with as little energy as you care to have. Depends on the size of your hammer, right? So you can make it break the frictional force and move, but it doesn't move very far because there's not much energy in it. Very important capability. It's called high technology. Okay, so there's the lens and its little holder. It's got little things to pivot it and support it. There's a taking lens off stage, and these are 3 copies of that funny little A-sphere in the middle. When we finally put all this stuff together, people said, well, isn't it amazing what that little lens did? Well, they'd forgotten we changed the eye lens at the same time. But the purpose to make a camera to fold up, and I just wanted to show you it worked. We made a camera that folded up. Okay? Now, the next part of our story goes to the taking lens. These are plastic taking lenses that were in another product. We made more than 70 million of these lenses. They cost less than $1 each in quantity. Three plastic elements. You focus by turning the front, which is screwed into the back. That changes the distance from the first element to the second. And that worked okay, except it didn't really lend itself very well to automation. If you want to drive that with an autofocus unit, you need a motor, you need an encoder, suitable clutches and stuff. You need to adjust it. So we didn't like that. So the first thing we invented was a camera that didn't focus. I think it was called a focus-free camera in those days. We made this mainly because our competition, the Kodak, was selling a focus-free camera, and it's, we can make it a little bit cheaper that way. But this is a meniscus camera lens, classic design, called a landscape lens, and we improved it by putting an A-sphere on the back and by using 2 apertures. We figured if that triplet lens is going to darken the corners a little bit, let's do that here because you can make the image a little better. So that's what that was about. We made an awful lot of cameras that way. There was something called the One Step that was the world's most popular camera for at least 2 years running. That was the white one with the racing stripes on it. But that wasn't quite good enough for us, so we made something else called the Model 660 that had a little wheel here with several lenses on it that could be rotated in position about an axle that would let us focus on 4 different zones. That kind of worked okay, but it had some limitations. The corners were a little bit too dark. There was a little more distortion than we wanted. And with only 4 zones of focus, it wasn't that great for focusing on scenes that got in close. So we thought we'd take a look at the spectacle lens art. This happens to be one of mine. But if you think about what spectacle lenses look like these days, they've got a gradient of power from top to bottom. So you can look downward and read and look upward and drive. And there are a lot of variants on that. This is a patent by Jim Baker, our lens designer, for a particular way of making 2 pieces that can slide by each other this way. 2 pieces that give a corrected image that can be very good for taking a picture. There's some prior art I'm going to come to. His differs from the prior art by putting a 5th order term in, and we called that quintic, which is where the word quintic came from on some later cameras. But basically, if you slide these pieces over each other, what you experience is a lens that's changing power from plus to minus. And obviously you can focus if you use that. As Jim pointed out, if you think about a pair of lenses with flat surfaces and curved middle, what you put in the middle can be a little different on 2 sides, and they can be A-spheres or spheres or whatever you need. And they don't change function much if you deform that airspace into a bit of an S-curve without changing its thickness. But if you've done that, and now you slide them, you get a focusing change. Over here, it doesn't change focus, it just changes how much prism you get. It changes the angle a little bit. So effectively, you're kind of moving up the ladder to changing focus. Now, that's the concept. We came out with a joint patent a little bit later, this back in 1987, for something that makes use of that concept, but instead of sliding it, it pivots it. Why? When you get down to the nitty-gritty of building a camera, let me tell you, it's much easier to pivot something than to make it move smoothly in a slide. Practical matter. It takes twice as much math and the part's trivial. Another illustration from it, you see it goes from convex to concave, and it's got a matching component. Now, you don't need to move both of them. So in the product, we have one that stayed fixed and one that moved. That's its axle. It pivots about that, pretty close in. And that's just a thick meniscus front element. Not terribly different from one you saw 2 cameras back. So what do you do with it? Well, here's a top view of the piece that's doing the focusing, showing that you can get several apertures over that same little width. That's only got 6 of them drawn, and ultimately we used 10. 10 different steps of focus using the same little area practically. So it was very compact. It was also a bigger area than we could have afforded on a wheel. You know, you try putting 10 lenses on that wheel and making them big, it's bigger than the whole camera. So again, we're talking practicality. I kind of like this view, which shows what the shape really looked like when we were working it. This is what you get if you take a profilometer that can handle a three-dimensional object and you look at the shape, comparing it to a flat. Now you notice the scale, that particular vertical scale is 20 thousandths of an inch or half a millimeter. Now, the next picture I'm going to show you is the error that's left over when you actually polish the part. Even at 10 times the scale, it's about 1/10 as big, which means that the error left is only about 1% of the power of the piece. So it's really pretty good. And gosh, what year were we doing that? We sold the product in '86, but we got this done a little ahead of that. Anyway, we made a lot of tools like this and molded a lot of parts. This is what a part might look like, reflecting a piece of graph paper, so you can see it's not exactly a flat from the distortion of the lines. And that little piece pushes out of this polishing holder and goes into the mold. There's another one, similar idea, slightly different shape. I think this was actually slightly earlier. But you can see it's a free-form surface. This is a neat machine made of granite that we use for this purpose. It's built in such a way that we've got slides moving crosswise. They're air slides. They're propelled by linear electric motors. There's a slide moving up and down. So we've got 3 coordinates. This was used for measuring things. And one problem you have with a machine like this is you don't want your servo and its magnets to hold the whole weight of the vertical slide. So what we have up here is a boat in a little tank that supported the weight, heavy fluid that just held it up. And you can see John Mader hasn't changed a bit since that picture was taken in the early 80s. Number of interesting properties here. We had a lateral travel of a whole foot, front to back, whole foot, right? Vertically half a foot. So well, it was a half a cubic foot, do I remember it right? Over which we could deal with precision of about 1/millionth of an inch. And this was early on. Not everybody had these back in 1982. The people who cut the granite used to manufacture tombstones, so they offered us any engraving we want, including a willow tree or anything suitable for the function. And we just were satisfied with a Polaroid logo and the date when it started. We never got back and carved when they took it apart and junked it, but that's another issue. But for a while, this was as precise as any machine that could do the same job. The measurements were made with a little direct contact, a little tiny ball, initially ruby, later something else, that would rest on the work. And it was positioned by a servo that made it contact with constant pressure. And we could move the work with constant speed and draw that profile very fast. And could make as many profiles as we wanted to do a three-dimensional job. There are multiple air channels here. The air pressure that went into the air slides was arranged so there was more on the bottom than on the top because the slide was heavy and we wanted to support it properly, top and bottom and sideways. So this really worked very well. And locally where you measure this thing, we had one glass ball we used to measure repeatedly, and whenever we tore a machine apart and replaced the components of it or made a new machine, we'd measure the same ball and make sure the radius hadn't changed. And it never did. It was usually good to 1/millionth or so each time. Here you can see what amounts to a flexural hinge, and there's a capacitor gauge that would tell us when the force was right. Right? And this is what the 3 parts look like for the so-called spectra camera. This is the one that moves to focus. This is that front meniscus, and this is a little back one that doesn't move. This also had some rotationally symmetric sphere imposed on it, as well as a little bit of positive power. These were taken by laying the parts on a glass plate a little bit above the graph paper, so you can see something going on. Okay, and a demo of the function. This is just a tungsten light bulb, one of these shutters, and the tungsten light bulb is focused over here on the screen. You see the little ends of a V-shaped pointer filament back before we had these. Now you notice it's blurry on the Kleenex box in the middle, and you notice that this little thing hasn't been pulled up. In this picture you can see that the little moving device has been pulled up, and you can see what that does to the imaging. It's now in focus on the Kleenex box, and it's blurry in the background. Now this is the mechanism that lets that camera focus from infinity down to 26 inches with just a lateral motion of that piece. Mechanically it's very clever because when you take the picture, you have a sonar ranging that tells you how far away the object is. And then there's a little kicker, the solenoid, that just makes that thing jump. And as it jumps and moves, a little sensor counts holes going by, little holes in its frame, and it knows when it's reached the right place, and a little latch comes in and stops. And compared to a normal shutter, about the only thing we had to add was the latch. No motor, no encoder, no junk that you would normally have to work a screw thread lens. Furthermore, they were all the same power, didn't have to be adjusted in assembly. They just were molded right and they went together. Now one question is, how do you test a thing like that? Well, if you're molding any kind of an optical part, that matters because the factory's going to run all 3 shifts and you're not there. This was a scheme that was thought up by Steve Fantone, who had just recently joined us at the time this came up. This is a way of using an interferometer to test a freeform molded part. Now, if you're going to test a freeform molded part, and you're going to use a hologram and an interferometer, there are a few different ways to make the hologram. The obvious way is you make the best part you know how to make, set it in an interferometer, and expose a hologram from it, and then compare other work with that. Okay, but maybe it's not that good. Another thing you could do is computer generate the hologram, which we calculated would take an awful lot of printer time in those days to produce. But he thought of a third way, got a patent on it. The third way is you take the hologram of the mold cavity, which of course is backwards. But when you have a hologram, you've got images on both sides. One's inside out and one's right side out. You use the other image, and it thinks it's looking at a lens when it's looking at the mold cavity or vice versa. So now you can do a direct interferogram to measure your freeform against what you thought you were trying to make. Of course, they'll never get better than your mold, but that's not going to happen anyway. Right? So what happens next? There's the camera. Looks pretty, doesn't it? They had various colors. I think Electrolux was putting the paints on. They had all kinds of problems making them like this. They had one called champagne that was about this color. And the way to get in trouble at the time was to say, champagne, huh, with all the bubbles? Because bubbles were one of the serious problems in the paint job. This camera is called the Vision camera, came later. I'm not sure, they're probably still available on eBay. And it's worth buying one just to see the 6-bar linkage work. Because when you open that camera, the case opens, the front opens, and a mirror comes up inside. 3 sequential things have to happen in one swoop. Like I say, buy it just to enjoy watching it. Somebody did a neat job on that. Anyway, within that camera are a couple more freeforms. This is the taking lens I think I mentioned to somebody. This part's acrylic and this part is polycarbonate. That's a very sharp lens. It's corrected for everything except for axial color. The red image and the blue image are something like 3¼ millimeters apart. That doesn't affect the sharpness of the picture at all, so it was the right thing to do. Everything else is sharp about the picture, taken that way. Now, this is a little bit like the SX70, but different. There's no intermediate aperture stop. The image comes down here onto a focus screen, bounces off the mirror, comes over here to a concave mirror, comes out to the eye lens. Because we didn't have the aperture stop, it had a different geometry, we made the mirror a freeform. And one of the eye lens parts is a freeform. Worked pretty well. We got a very sharp view through that camera. Unfortunately, it had some other dumb things like a great big storage compartment for the pictures that made the camera bigger, for no apparent reason, because the pictures would easily fit in your pocket. But it's worth mentioning that in grinding the components for this was the tool for the mirror, wasn't it? By this time, we weren't using a spherical tool anymore. It was toroidal for a variety of reasons. You make it bigger, it wears slower. Anyway, when you grind a thing like this, you make a lot of passes. You get to something you can shine up without too much trouble and mold. And that's the way it was used. Where it's pushed up just enough so you can see it. It was flush when it was being polished. All right, these are the molded parts lined up. The mirror, 2 eye lens pieces, and that's just a retainer clip that held the mirror in. Let me tell you, lots of problems can occur when you glue things. If you use metal clips, you don't have those problems. Now this is a big machine that we made later. And what happened was, I told the guys we ought to start using our 3-dimensional measuring machine for generating shapes as well. And I was told that that would be terrible to use the world's best measuring machine for grinding stuff up and getting all cruddy. And I said, no, you got it backwards. You're using the world's best generating machine for nothing but measuring. And this went on for a while, and we managed to satisfy each other by building a new machine. These floor tiles are 9 inches across, so you can kind of estimate the size pretty quick. That's big. remember the Star Wars show? We called this the, what was the Wookiee Stomper or something? But it's made of granite. It's got air slides in all directions. It's upside down compared to the other one. This thing is like a moat. It's a tank that holds a high-density silicone fluid and has a float in it of similar size that's used to hold the heavy vertical slide up, so we don't have anything in the way above it. So again, it's a 3-axis machine with rather beautiful control. Look at it from the angle, you see all kinds of air gauges and controls. You see linear electric motors. That works very well. They were initially designed for us by a professor, it was at Harvard, I think it was, who been gone for a long time. But his claim to fame was back in the days of the Manhattan Project and the A-bomb tests. He was the young guy they sent up the tower to disconnect one of the dud A-bombs. So, anyway, when we knew him, he was designing magnetic motors. All right, look at it from different directions. It's got rubber sheeting to keep the mess from going where it shouldn't go. There's a table, flat table here that holds the grinding spindle, and over here is a plate that holds the work in some way. That can move in and out. It can go left and right, and this front table can go up and down. So count them, all 3 coordinates are represented. This shows something we had to do. This is the grinding head that's going to grind this work. If that's not a good spherical or toroidal shape, you're going to know it because your part's going to be bad because you transmit whatever the shape of the grinding error is onto the work. How do you avoid that? The shop told me they wanted to buy a new machine for dressing the grinding wheel. I said, nonsense. You put another spindle in our machine, it's going to give you a better result for less money. And after 6 months of begging, I got what I wanted, and they could generate the proper shape of that wheel against this other spindle whenever they needed to. It worked pretty well, didn't it? So, anyway, this is a part. Again, it's the Spectra focusing lens done this way. What's interesting about this one was it wasn't polished. That's a ground surface. You know, nobody would ever let me put one in the mold without polishing, even though it would have worked fine, because the grind still isn't cosmetically what it ought to be. If you shine just a laser beam onto that ground part, you get a lot of spots. It thinks it's a diffraction grating because the error is reasonably periodic from all the passes that were made. But it's very shallow. The results are quite good. We took this with an interesting imaging technique called photon tunneling microscopy. That's got a vertical relief of only a micron. I mean, a wavelength is about 0.6 of a micron, so this is sub-wavelength. And that's 1,000th of an inch there. That's greatly contracted compared to the vertical height. So this is what that process leaves behind. If you measured it, typically we got, about 2 millionth RMS error for the area. And you shine it up a little bit, make it look pretty, it's down to about 1 millionth. So that was very good 3-dimensional control, and that's what we were doing with it. People built machines like that since for what they call conformal optics and other kinds of freeforms. But we use that for some of your stuff and things. Now, I mentioned some history. This is a British patent from 1926 that refers to a Japanese patent from 1925. It names an inventor who was named Kitajima. I think that means North Island in Japanese. And the thing that's interesting about the British patent is it explains where he lives in Kyoto, or where he lived at the time. 48 Fukumoto-cho, Neumandori, Shintakakura. There's a streets in Higashiro, Kamikyo, Kyoto, Japan. Well, in 1992, we happened to have gotten to Japan on a trip to Osaka Sunday afternoon with nothing better to do. So we took the bullet train over to Kyoto, it's about 15 minutes, and went to this guy's old neighborhood just to see if we could find it. And one thing that's always impressed me about Japan is if you walked up the information desk in a hotel, they've got a set of books, atlases. They can tell you where everything is in all the other cities in Japan, including the restrooms and the railroad stations. It's so documented you wouldn't believe it, but unless you can read Japanese, you don't know this. The young lady we talked to gave us a map of where this guy lived, so we knew where to go to get there. I'll come back to that. Birchall patented something in 1935 for sliding 2 lenses over each other to focus. He didn't have the math quite right, but he had it on the right track. This guy Lewis in 1941 did the same thing with slightly different arrangement. This stuff's been around forever. Alvarez, you've heard of the Alvarez lens. Alvarez patented the same thing in 1967, where you slide two of these things over each other for focusing. Jim Baker did his a little bit later. I've shown you that, so I'm going to show you where Kitajima-san lived. We went into Kyoto, took the subway up to about here, found the right street, walked across a few blocks. It was getting dark, so we were hurrying over here. And we found this is the intersection of streets that that patent names. Okay, so there's the station for the bullet train. That's the street sign we identified could match with the map. Walked by some buildings that may have been there when he was there in the 20s. We came to this corner. This is a corner that's a named intersection. And the way it works in Japan is they've got a poster in a neighborhood. It's got a little map naming everybody and showing them where he lives. Unfortunately, there were no more Kitajimas present. The whole family's gone now from that area. But we have the names of everybody still living there. Number 48 isn't the location really the way we do them here, where you build them in sequence. They used to number houses in the order they put them up, so the numbers were all over the place. So I have no idea where 48 was because we had no way to even hope to find it. But we did find a temple around the corner that I'm sure was there when he was. So, you know, this is a guy's old neighborhood. He certainly deserves some credit for what he pulled off in the 20s. It's a paperweight they made to help discuss what these shapes look like. And now we come to the new patent for manufacturing this stuff, and we're just going to make it. Okay. This was patented in September '09. It's got a number if you want to copy it down. Basically, you have a plunger and an anvil, and you put powder in between and squeeze the heck out of it, and that makes it a solid. There's some powders that work very well for this. The one that's preferred by chemists for the last few decades is potassium bromide, and they use it for a measuring technique. Now this shows it being mounted, being compressed into another kind of cell. I'll give you more definition in a moment. Everybody knows what thermal imaging is all about. If you take the picture by thermal emission, you can see things that you can't see in dim light. You can see what parts of a car are hot when it's been running. You can see where the engine is in a helicopter and maybe shoot something at it. And this has been done with a bunch of different kinds of lenses. This particular lens design was just a simple attempt, one that would make a simple objective lens using germanium. Simple design. These germanium pieces have A-spheres on both sides, so you diamond turn them to make them. These are just three different axis angles. You get a pretty good image. Pretty good being, these are the spot diagrams compared to a circle representing what they call the airy disk, which is a good diffraction image. So they're not bad for two elements. That's the modulation transfer function, and these are for different angles. 15 degrees off axis is the lowest one. But that's the way you normally would judge a lens design. On the other hand, if you make the lens the way I'm proposing might be good to think about, there's still two germanium lenses. They've gotten a little bit flatter, a little bit thinner maybe, and this one's the one I molded out of potassium bromide. It's got A-spheres on both sides. Germanium lenses have spheres on both sides, which means you can buy them from anybody who can make camera lenses. Okay, I've priced them. It would cost me $30 or less a pair to buy a pair of finished lenses like that made in China. Not half bad compared to what people are charging for these assemblies. Now, if you compare the function, they're more alike than different. I wouldn't say this is highly tuned up because I'm not a professional lens designer. MTF is slightly lower, but not bad. I would say that it competes very well as a design. For the other things, it's distinctly cheaper. It's a little bit smaller. You can see there side by side. Happens to be a little bit more telecentric, if that matters. That means that the light hits more directly perpendicular to the sensor surface. Distortion's a little better. It's easier to mount the thing. And the F number is a little bit lower. The beam's a little bit fatter there. If I made the beam the same size, the MTF might come up. So this is the argument that you can make a perfectly plausible lens. Now, what else is different? If you want to put a wavefront encoding device in, you can put it maybe someplace on one of these surfaces at the same time you're molding the lens. Right? That could be anything you need. So I believe that that lends itself to cheap, high-volume manufacture with any shape you want. Samples I've made, just for proof of concept, involve this hand press, which is about 1.5 feet long. And these are the pieces that come with it. The anvil, the piston, cylinder you put together. You dust a little powder and you squeeze it. Now when you're using this, it's a little bit tricky because the pressure you're putting on depends on how much powder you put in. A little hard to calibrate. If you put too much in, you can't really squeeze it over center as far as it should go. But you can put a lot of force in. Now at the time I did this, I didn't have any of the nice old freeform molding tools we used to enjoy and have all around us on our desk. I think I gave my last set away when somebody wanted to manufacture one of those cameras. But you notice that these are all the same size as one of these. They're in a bag as I was traveling on a plane, but we're talking about a 25-cent piece that costs exactly 25 cents. And the thing that's interesting about that 25-cent piece is you can cram it in here very nicely. I think I use one of the other parts just as a spacer, and use that as a molding tool. And that's not half bad because it's freeform. There's an area here that's partly concave and partly convex. You can see what certainly is equivalent to an array of little cylindrical lenses that are kind of bent in a curved shape. And there are even some fine scratches that behave about like the lines on a diffraction grating, for example. So all the things we need are really right there for 25 cents. I didn't have to go beg anybody for a tool out of a private collection or anything. It wouldn't have fit anyway. When you squeeze one and take it out, this is the kind of thing you get. That's a reflected light, and it shows those features of George Washington. This is a picture from prior art showing putting together one of these things for the long-time commercial use for sampling. Oop. This shows my way of using it. One embodiment is to mold the lens directly into what's going to become a lens cell. All you have to do is turn it 90 degrees and put additional lenses if necessary in front and back, and it becomes your assembled lens. You don't even have to handle that thing, much less pull it out. Now, there are various things you want to do. If you're not putting lenses around it, you may want to coat it with something to keep humidity away from it, because these are materials that can dissolve a little bit. And you can do that. You can spin coat it with something like dissolved polyvinylidene chloride. You can use a gaseous coating technique, coat it with something called perylene, or you can grab some saran wrap from your kitchen and it's polyethylene, put a little bit in front and back and grip it in the cell with that. Any way you do it, you can seal it up so that moisture can't get to it anymore. So the question of moisture is really minimal. This is that same piece I showed you before, but with light coming through it. You see it's transmitting light. You can see some pretty fine detail. You can also see just the finest traces of some of the particles that weren't quite squeezed together. It's a little bit hazy looking, but that's for visible light. When you go into the infrared, the scattering improvement goes, like for the blue sky, inverse fourth power of the wavelength, so it goes away rather quickly. Close up a part of the structure. You can really see every detail that was on the metal. Somebody asked about wavelength range. These are wavelength in microns. Visible's down here and stops about there. This actually goes into the UV a little bit. You probably scatter too much, but you could use it. Goes out to 20 microns before you'd start to drop off. Somebody asked about table salt. That goes out to maybe 10 or 12, and then it drops off in a more gradual way, but table salt doesn't stick together quite as well. Okay, that cesium iodide doesn't start out quite so well in the visible, but it goes out to 40 or 50 microns you could use. The guy who published these graphs, Dave Tosi, this was in the Photonic Spectra Technical Handbook they put out every year. He forgot to mention how thick the samples were, so I'm not sure I do exactly what that means, but the information's available. Now, this I think is a 2,000-ton press you could buy off the shelf from a company called Beckwood in St. Louis. They make other sizes to order. And I think this would be capable of providing the pressure we need out to a diameter pretty close to a foot if you really were crazy enough to go that big. As the recommended pressures run from 25,000 to 60,000 pounds per square inch. And 2,000 tons will get you a lot of pressure, a lot of square inches. Okay? So that's where we are. Some of the stuff's on my website, but not this particular set. Okay? Okay, questions? Nobody heard a word. Yeah.
How the heck did you do the optical designs of all those freeform surfaces before you had a Z-Max sitting on your desk here?
Well, remember I was working with one Jim Baker. And Jim Baker hasn't been much publicized because a lot of stuff he was working on was not well known. But he did the optics for the U2 camera that used to go overhead. may still for all I know. He did the optics for the SR-71, hand-figured the best set in a little plywood enclosure. He used dark green paint on because he didn't have black. I mean, this was a phenomenal guy who lived to about the age of 90, was sharp the whole time, and was able to do some of the world's most incredible optical designs. One of them was the famous Baker-Nunn satellite tracking camera that I think they may still be using. I think they maybe retired them. It was a Schmidt camera with not one Schmidt plate, but three spaced out to do a little better correction, with a huge beam aperture that could track the smallest little satellites going across. There were a dozen of these around the world. There's one in Australia, and they spread them around so they could catch anything going by in space. And they used these for many years for mapping all the junk. But he was one phenomenal lens designer, and I had the pleasure of collaborating with him for something over 30 years. He also did work for other people he couldn't talk about. There came a time when the U-2 was declassified, and he could show us a lot of details about that. The first picture showed him standing next to, I think it was the director of the Smithsonian, next to their exhibit in the Smithsonian Air and Space Museum. That's how public it got. But that was an incredible lightweight design. He still considered that the toughest one he had done. But he and I kind of resonated. We did a lot of things together, but we mostly had different patents. We had one joint paper and one joint patent out of all those years of collaboration. But we each have a slew of the ones that were collaborative. Okay? And he was also one of the first people to use computers in designing lenses back in the 40s. He started out with a Marchand calculator and moved up as better stuff became available. Anybody else? John, Don, will you hold your hands up so people will know what kind of people actually did a lot of this work? They're the guys who made a lot of it happen. We had a team of, gosh, I don't know, about 15 people when you count them all. There was Jim Baker, there was myself, there was Stan Haskell, there was Tom Loftus, there was these two guys, Nick, Walter. We had a whole mess of people, none of whom could have done anybody else's job. And what was interesting to me was it all went smoothly. I don't recall any time when any of us pointed at somebody else and said, you did this wrong. Did that ever happen? I don't remember it. And it all happened. So, yeah. Of course not. This was in Cambridge, Massachusetts. I mean, there's another company that was doing things in Rochester, but it wasn't very imaginative. They didn't know how to do instant photography until we showed them. Yeah. Anyway, any more questions? I've probably outworn my welcome by this point.
So let's thank Ms. Plummer again.
Yeah. Thank you.